Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. Today, the topic which we are going to discuss is about the mass flow rate and characteristic velocity of the gases which are leaving the nozzle. So, coming to the overview of today's presentation, today we are going to discuss about the equation. We are going to generate an equation for the mass flow rate in terms of chamber parameters, that is pressure in the chamber, temperature in the chamber, and also with respect to the nozzle parameters. And also we'll generate an equation for the characteristic velocity also. So coming to the topic, mass flow rate generated by the gases leaving the nozzle. Here you can consider a nozzle here, convergent divergent nozzle. Okay, here you can see a CD nozzle, and here is our throat portion, and the mass flow rate, if you consider the mass flow rate with the symbol m dot n, and this is the exit of the nozzle. Area at the throat is 80, okay, 80 in terms of meter square. So coming to the basic formula of mass flow rate, the mass flow rate m dot through a nozzle from an area of 80 can be written as m dot is equal to rho AV. So there is a basic formula, that is m dot is equal to rho AV. From that, if you write the mass flow rate through the throat, from this at that particular section at the throat, we calculate the mass flow rate. That mass flow rate is equal to density at the throat, that is rho T, and area at the throat, and velocity of the gas at the throat. So the equation will be m dot is equal to rho T AT VT. From the basic formula, m dot is equal to rho AV. So in this formula, we have parameters density, area at the throat, and velocity at the throat. But I want to convert this formula in terms of pressures and temperatures in the chamber. So if I know the pressure in the chamber, and if I know the temperature in the chamber, and if I know the parameters in the combustion chamber, then I want to calculate the parameters. I want to calculate the m dot easily with the parameters of combustion chamber. So that's what we are going to do now. So the parameters, right? Rho T and Vt denote the density and velocity at the throat, and AT is the area at the throat. So if you apply the ideal gas equation, okay, apply ideal gas equation at the throat. So the ideal gas, according to the ideal gas equation, we can say P is equal to rho RT. P is equal to rho RT. Pressure is equal to density into gas constant into temperature. So from this equation, we can write an equation for the density at the throat. Density at the throat. So if you write the equation for density at the throat, rho T will be equal to Pt by RTT. Okay. So this equation will turn to rho T equal to Pt by RTT. So here Pt is the pressure at the throat, Tt is the temperature at the throat, and R is the gas constant. Okay. Gas constant of the gases at the throat. Universal gas constant. Here we got one equation for the density rho T in terms of pressure and temperatures. The next thing is parameter A, area, right? Area at the throat. So area cannot be related to pressure and temperature. So we cannot generate any equation for area in terms of pressure and temperature. So the next one is velocity of the gases at the throat. So for this we can make an equation in terms of pressures and temperatures. So if you consider a steady state one dimensional adiabatic flow, okay, if you consider a perfect gas and steady state one dimensional adiabatic flow in the converging portion of the nozzle, okay, according to the one dimensional steady state equation, we can write the total enthalpy. Okay, enthalpy is constant. So if you take the enthalpy, okay, specific enthalpy CpTc, that is a enthalpy in the chamber and enthalpy of the gases at the throat. So if I consider this enthalpy, total enthalpy is constant because it is an adiabatic. Okay. Then enthalpy in the combustion chamber can be written as CpTc. So there is an equation, right, for specific enthalpy, that is Cp into temperature. So from this equation, if I write the enthalpy in the combustion chamber, then it will be Hc is equal to Cp into Tc. Okay, the total energy, right? So and next the energy, this energy will, some of the enthalpy, okay, some of this enthalpy will be converted to kinetic energy when it comes to throat. So the total energy is equal to, at the throat, it is a sum of enthalpy at the throat plus kinetic energy of the gases gained. Okay, so if I write the equation for enthalpy at the throat, then it will be Cp into Tt and kinetic energy per unit mass. Okay, that is half, kinetic energy is half m Vt square at the throat per unit mass, right? So I can cancel this m, then it will become half Vt square. So the same equation written here. So this is the steady energy in the combustion chamber, energy of the gas in the combustion chamber. This is the energy of the gases in the at the throat. Okay. If I take a Cp common here, then you will get 1 Cp in the denominator. Then this equation can be written as Tc is equal to Tt plus Vt square by 2 Cp. Okay. Now I have written a equation for the temperature in the combustion chamber with respect to temperature at the throat and with respect to the velocity at the throat, velocity of the gas at the throat. And further I can simplify this equation by substituting the value of equation of Cp, specific heat ratio at constant pressure. Okay, specific heat at a constant pressure. So this Cp can be written as Cp is equal to gamma minus 1 by gamma R. Cp can be written as, gamma R by gamma minus 1. Cp can be written as gamma R by gamma minus 1. Since we have 1 by Cp here, this can be written as gamma minus 1 by gamma R. Okay. After taking Tt common here. Okay. So this is the final equation we got. If you take Tt common here, Tt will come out and it will be 1 plus Cp will become gamma minus 1 by gamma R, into 2 Tt into Vt square. If I consider this is the velocity of the gas at the throat and observe this term gamma R Tt. Okay. So this is an equation. A is equal to, there is an equation for the speed of sound, that is under root gamma R T. So this term is similar to this. So if I substitute this, then I will, that means this term is giving the velocity of sound at a throat. Okay. And if we observe this term and this term, this will be velocity and divided by sound. Velocity divided by speed of sound. This is nothing but Mach number. So I can write these two terms as Mach number. So 1 plus gamma minus 1 by 2, 1 plus gamma minus 1 by 2 into mt square. So this equation will turn to 1 plus Tt will come out, it will be 1 plus gamma minus 1 by 2 mt square. So now this equation is in terms of temperature at the throat and Mach number at the throat. Okay. The temperature in the combustion chamber can be written as in terms of temperature at the throat Tt and Mach number at the throat. Now I want to make this equation as a ratios between the temperature in the chamber Tc and the temperature at the throat Tt. So if I write the equation like that, okay, if I write the equation like that, before that I can substitute one thing here, that is mt. Here we have Mach number at the throat. So there is a condition, throat condition for a convergent divergent nozzle. Everybody knows that. So always Mach number at the throat should be equal to 1. By default, the Mach number at the throat should be equal to 1, then only the gases will be further accelerated. The velocity will be increases in the divergent portion. Otherwise, the velocity will be decreased. Right. So, if you substitute that condition that mt equal to 1 at the throat, then the equation which we get, okay, Tc by Tt, okay, Tc by Tt, this Tt will come down, Tc by Tt can be written as 1 plus gamma minus 1 by 2 and substitute here equal to 1, okay, 1 plus gamma minus 1 by 2, and this equation can be further written as gamma plus 1 by 2, okay. Finally, the equation is Tc by Tt equal to gamma plus 1 by 2, and we have an adiabatic relations. There is a relations between the temperature ratio and pressure ratio. From that we can write pressure ratio P2 by P1 is equal to T2 by T1 whole to the power of gamma by gamma minus 1. Okay, the similar way this Tc by Tt and relation between Pc by Pt can be written. Okay, so that is Pc by Pt is equal to Tc by Tt whole to the power of gamma by gamma minus 1. Right. Now we have equations. One is a temperature ratio. We have an equation for temperature ratio for the combustion chamber to the throat, and we have another equation for pressure ratios from combustion chamber to the throat, and also we got one more equation in the previous slide, that is density at the throat equal to pressure at the throat divided by RTT. So now we have to substitute all this in the m dot equation. Okay, and before that I want to simplify that. So this is in terms of pressure at the throat and temperature at the throat, but I want to turn this density equation rho T in terms of parameters at the combustion chamber. So what I want to do is I want to rewrite this equation. I want to rewrite this equation as rho T is equal to Pc by RTC into Pt by Pc pressure ratio and Tc by Tt temperature ratio. Okay, so here you can observe this. Pt is as it is here. Okay, Pt is as it is here, and RTT here, R and Tt, these are as it is. Okay, only thing is I have made Pc, I have written Pc in the numerator here, okay, and Pc in the denominator here. The same way Tc in the numerator and denominator. But I have rearranged the terms. So that I want to write this equation in terms of temperature ratios and pressure ratios. We got another equation for velocity of the gas at the throat. So since Mach number at the throat equal to 1, and we know the equation for the Mach number is velocity at the throat divided by speed of sound at the throat. Okay, that is equal to 1. So from this we can write velocity at the throat is equal to speed of the sound at the throat, and speed of the sound at the throat formula is under root gamma R temperature at the throat. So even we got the equation for velocity of the gases at the throat also. So the basic equation for m dot is equal to rho T, At and Vt. So we got one equation in terms of pressure and temperature for rho T here, and we got another equation for velocity at the throat. This is another equation, and area we substitute as this. So if you substitute this rho T here and this Vt here, then we will get the final equation of mass flow rate through a nozzle in terms of temperatures and pressures. Let us write that equation now. So this is a basic equation, right? M dot is equal to rho T At into Vt. So these are the formulas which we have derived now. So this is a basic equation, and we got one equation for density at the throat, and this is another equation for velocity at the throat, and this is the pressure ratios. So substitute this in the m dot. So what do we get? If you write m dot equation here, m dot is equal to, substitute rho T. Okay, substitute this in the rho T, then it will become Pc by RTC into Pt by Pc into Tc by Tt. Now next At. So I will write area of the throat. Next, velocity at the throat. So what is the equation for velocity of the throat? This is the equation. So into gamma, okay, under root gamma r tt, under root gamma r tt. So now I want to substitute. So here Pc by Pt relation is there, right? And here you can see Pt by Pc, okay, and also Tc by Tt. Okay, so if I write this Pt by Pc, in terms of Tc by Tt, then the whole equation will be in terms of temperature ratios with respect to combustion chamber and throat. That is what I want to do. So now I want to rearrange these terms here. So the chamber pressure here Pc already, okay, Pc, here I am writing Pc into this At, Pc At, and if you observe here Pc At by, here you have r in the denominator and root r in the numerator. So if I cut this, then it will become under root r, okay, and next here you have under root gamma. I want to write this under root gamma here, okay, this is also over, and next this r I have written, okay, and next here Tc by Tt, and also one more term is there, T under root Tt is there. So if I want to, so this is under root Tt, and if I cut this under root Tt with respect to this, then it will become under root Tt. So I want to return this under root Tt here, okay. So this equation will become Pt by Pc into 1 by Tt. This term under root Tt. Next, so I want to write this Tc term as Tc power 2, and I want to cut under root Tc. Then I will write here under root Tc here and into under root Tc here, okay. This Tc and this Tc I am returning as under root Tc and under root Tc. Okay, so finally what happened? This equation become Pc At divided by under root r Tc into under root gamma and Pt by Pc. This Pt by Pc can be written as Tt by Tc whole to the power of gamma by gamma minus 1 into Tc power 1 by 2 divided by this one Tt power 1 by 2. Okay, so here if you simplify this equation, Tt power, here see here, Tt power gamma by gamma minus 1, Tt power gamma by gamma minus 1 divided by Tt, this term and this term, will become Tt power 1 by 2. What happens? This equation will become Tt power gamma by gamma minus 1 minus 1 by 2. Okay, if I do this simplification, okay, gamma by gamma minus 1 minus 1 by 2, this equation, this can be written as 2 into gamma minus 1, okay, gamma will be as it is, okay, gamma minus 1, okay, this will be 2 gamma minus of gamma plus 1, okay. So this can be written as, this 2 gamma minus gamma will become gamma plus 1 by 2 into gamma minus 1. Okay, so whatever this equation can be written as, this equation will become Pc into At divided by under root Rtc into Tt power gamma plus 1 by 2 into gamma minus 1. The same way we can write for Tc also, Tc power gamma plus 1 divided by 2 into gamma minus 1. Okay, So finally we got this equation. So if I write this equation, okay, so this is the expression which we got finally. So m dot is equal to under root gamma into PCAT by under root RTC into TT by TC whole to the power of gamma plus 1 by 2 into gamma minus 1. So this is the equation which we got in terms of chamber pressures and chamber temperature and temperature at the throat. And we have an equation for TC by TT also, that can be substituted here, that is gamma 2 by gamma plus 1. If you further substitute that, then finally what happens? So after substituting this m dot will become, okay, so this m dot will become under root gamma PCAT by under root RTC into 2 by gamma plus 1 whole to the power of gamma plus 1 by 2 into gamma minus 1. So what I am doing here is, so there are so many terms in terms of gamma here, this term in terms of gamma, this term also in terms of gamma, and this total term is in terms of gamma. So what I want to do is, I want to write this total terms in terms of gamma as tau. I want to write this total terms which are in terms of gamma as tau, that is under root gamma into 2 by gamma plus 1 whole to the power of gamma plus 1 by 2 into gamma minus 1 as tau. So then finally this equation, if I write this, if I substitute tau here, then m dot will become, m dot is equal to tau into only the left terms are PCAT by under root RTC. So what is this tau? This tau is in terms of, tau is a parameter in terms of gammas. Okay. So the chamber pressure PC, from this we can write the equation for chamber pressure. Then this is the mass flow rate equation, right? From this we can also write the equation for chamber pressure, that is under root RTC by tau into m dot by AT. So whatever the parameter under root RTC by tau can be written as C star, which is nothing but characteristic velocity of the gases, and the units are also equal to the velocity. So this term under root RTC by tau can be written as characteristic velocity, and this is the equation for mass flow rate. So this is about the topic mass flow rate and characteristic velocity of the gases which are leaving the nozzle. Okay, if you observe this, m dot has parameters, one is in terms of gamma, and this is chamber pressure, area at the throat, and temperature in the combustion chamber. Okay, pressure in the chamber, temperature in the chamber. Okay, if I write the combustion chamber, so we should know the pressure in the chamber, and we should know the temperature in the chamber, and one more thing is we should know the area of the throat, AT, and gamma, specific heat ratio of the gases which are leaving the, which are the products of combustion. Then automatically we can calculate the m dot, the mass flow rate of the gases which are leaving the nozzle. So if you know the m dot and if you know the Vj, then you can calculate the rate of change of momentum of the gases leaving the nozzle, m dot into Vj. So this is about the characteristic velocity, and this characteristic velocity is very important term. So this C star indicating the capacity of the propellants to generate the gases and pressurize the rocket chamber. So it will explain the capacity of the propellants to generate the gases, and also it will explain how much extent we can pressurize the chamber. Okay, so it is therefore an index of performance of the propellant. So this C star is, we can consider this C star as the index of the propellant. So how effectively the propellant can pressurize the chamber, that can be explained with the help of this C star, that is characteristic velocity. And here we can also see the graph. So variation of C star with the temperature and specific heat ratio for a given molecular mass of 20 kg per kilomole, and here see this is the temperature of the chamber on the x-axis and characteristic velocity on the y-axis. As the temperature in the combustion chamber increases, you can observe the C star value is increasing for different, this is for gamma equal to 1.1, this solid line is for gamma equal to 1.1, and this dashed line is for gamma equal to 1.4. So as the temperature in the chamber increases, C star also increases. So even we can say as the temperature of the chamber increases, the pressure in the chamber also increases. So if you get more pressure in the chamber, so there is a atmospheric pressure A, right? There will be more pressure difference. As the pressure difference is more, you will get maximum kinetic energy for the gases. The kinetic energy of the velocity gained by the gases will be more if the pressure difference is between the chamber and the nozzle exit are more. And there is we can also write the mass flow rate in terms of characteristic velocity. So that is m dot is equal to PCAT by C star. M dot is equal to PCAT by C star. Chamber pressure, area of the throat, and characteristic velocity. That's it. And C star also can be written in terms of m dot. C star is equal to PCAT by m dot. This same equation has turned one. This is in terms of m dot and this is for C star. PCAT by m dot. So this is about today's topic regarding mass flow rate and characteristic velocity. Thank you.